Hi everyone. So today it is our great pleasure to have Julie Digne in our seminar today. She is a CNRS researcher at LIRUS, University of Lyon. She received her master's degree in applied mathematics from ENS Paris, and her PhD in 2010 from the same institute, for which she received a PhD award for the Foundation HUDMOP. In 2018, she defended her habilitation at University of Lyon. In 2011 and 2012, she was a postdoc at INRIA Sophia Antipolis in the Geometrica team, working with Pierre Elie and Matthew Desbrom from Caltech. Her main research interests are geometric processing and shape analysis, mainly when the surfaces are represented as point clouds. This includes surface denoising, meshing, scan merging, and surface segmentation, building either from surface PDE or building point set dedicated machine learning techniques. Her research results are published in leading conferences and journals in computer graphics and applied mathematics. She also serves as a member of several international programs committee and as an associate editor of Computer Graphics Forum and Computers and Graphics. In 2021, she was a co-chair. She's the co-chair of the technical paper program of SGP 2021. So with that, it is my great pleasure to have Julia begin her talk.
Well, thank you for this introduction. So it's a great pleasure to be giving this talk for the WIN seminar. Since there are not a lot of us here, maybe if you have any questions, feel free to interrupt anytime, and I'll be happy to clarify. Also, it's rather a long talk, so if I don't make it to the end, it's completely okay. So my talk will be how to encode, analyze, and improve 3D shapes. And what I mean by 3D shapes is data coming out of real object data, coming out of a process, a 3D acquisition process, such as a laser scanner or stereoscopy, or basically anything that can turn an object into a digital surface. So here what you see is a high-resolution laser scanner, which is acquiring point by point an archaeological surface. And there are several ways of acquiring surfaces, and there are also many different ways to represent data. And you can represent it as surface meshes, so sets of triangles which are joined by edges. You can just give them as raw data, just a set of points corresponding to acquired points on the surface. And you can also represent them as a set of voxels. But then you have data. Here I will focus basically on point sets mostly. Here you have data that can have different kind of accuracy and can represent things at different scales. For example, here you'll see an example which is acquired by a high-res laser scanner on the left. In the middle, you have a range laser scanner, a whole city acquired by a scanner which is put at several spots in the city. And on the right, you have the results of stereoscopy. So you take several pictures of a scene, and then you are able to reconstruct the 3D. And all these data have different kind of challenges, and they have different kind of accuracies, and you still need to have robust algorithms to process them. And this talk will be an overview of what I did in this area, and what I and my coworkers did in this area. And my first focus will be on something which is called self-similarity, which is a concept which I use to better analyze and represent the surface. So it stands for an object having repeated details all over itself. For example, if you take this spark picture here, you see that there is some pattern. The texture is the same at different places of the picture, and it's the same for this kind of rock. You have some features that are repeated. They might be slightly different, but there's some kind of statistical repetition, which is something we can try to leverage for a better analysis. And it can be, this self-similarity can come out of a natural process, like for this spark, for this rock, but it can also be part of a of man-made design. For example, here is a picture of Lyon, which is the city I live in, and you'll see that windows are repeated at same interval. And something very important for design, you want to have as many symmetries, as many repetition as you can. Well, not as many, but you want to have the right amount of repetition so that it feels better for the viewer, and it's better. It's more natural for a human being. It can also come from the design process. So here you see on the bottom right, you see a mask, and there are some repeated details in the hairs. Here you have this braid here, which obviously has some repeated elements, and that's also something which is something we are going to be able to take advantage of. So how do we capture the self-similarities? Because we have these virtual surfaces, which in this case will be just a set of points, maybe equipped with a normal, a vector, which is the normal to the surface. And how are we going to capture it? The idea is that if we have a single acquisition of a shape with a repeated detail, then it's equivalent to have several acquisitions of the same detail. And if we can make this small details, small acquisition talk to each other, then we'll be able to improve the quality of the scan. So we need two things. We need first a way to compute a description of neighborhoods. And second, we need a way to assess how similar the neighborhoods are. So basically, you're going to look at points on the surface, compute some description of what lies around them, and then compare this description between each other. So we will extract the similarities either explicitly or implicitly, and we will see how that's in which case we are explicit and in which case we are implicit. So let's just have a first look at what we started doing. When we have a surface, like a real surface, then we'll need to make some mathematical assumptions, small assumptions, for it to work in practice. So first, we'll have a topological condition, which means that a surface can be covered by a set of topological disks. So it's actually just the definition of a surface, mathematical surface. We'll also have a sampling condition. So remember, our surface is just a set of points, of 3D points. So we'll require that the neighborhood of radius R being the radius of a small ball centered on the point, we will assume that it contains enough points to make some statistical analysis. And then we'll also assume that the noise level, meaning the way the measurement error we did on the point, is below the radius, because otherwise we can't say anything. So we'll have to assume that we have a radius which is large enough for the noise to be included inside it. And we'll also assume that we know how to compute a local frame, so local coordinate frame. And this is the two first tangent directions and the normal for each point P of the surface. it's actually a huge issue, but I'm not going to go into the details. So we'll assume that we know how to parameterize locally a point. We have the normal, and we know how to compute two directions, which are the principal curvature directions. That means anything to you? Otherwise, just assume we have some way of computing a frame, a local frame for each point. So local shape description is something that has been known for actually very, very long. And it was actually designed in the beginning for partial or complete surface matching. Like you have two scans of the same objects and you want to put them, you want to merge them to have to compute the full surface. And there is a wide literature on how you can compute descriptions. And initially, it was okay to just have some destructive description, meaning that once you had the description computed, you could not go back to the initial to the surface. It would just give you some description, but it would not be invertible. And here we will use them to compare neighborhoods of points on the surface, and we will also require them to be invertible in the sense that we can go back from description to surface and not have lost the link. So here you have a famous example of a description which is quite used even still now. There is a description which is kind of natural if you think of it, which is a height field over some smooth surface. Why is it natural? Because it's a way you would, if you were the point living on the surface, it encodes how you would see the local landscape around you. And in terms of how it would be a valley, a hill, or things like that. So if you have a way to encode how the surface deviates from some smooth surface, then it can be a good candidate for a description. So the most natural one would be to just compute the tangent plane to the surface and then encode how much the surface varies with respect to the tangent plane. And if you see that as a small image on the surface, then you can encode it as a vector. Each bin has a height value, so it gives you a vector. And to compare the descriptor, you can use any metric you like between vectors in R2, in RD, D being the dimension of the image. So if you take a descriptor of size 4 by 4, you would need a metric between vectors in R16. So it's actually quite efficient and it's actually quite simple to compute, but there is some issue which is that it cannot really capture similarities when there's some large-scale curvature. So, for example, here, if you have a look at this red curve, you see that there is some detail, but it's bent over some surface. So computing the difference, the deviation to a tangent plane is a good first step, but you might not find this description to be similar to the same detail which would be bent around another type of surface. For example, so one way to solve that is to consider a Quadric+height descriptor. So you fit a quadric around the surface, and then you have this height which measures how you deviate from this smooth surface. You will also get an image. You will also need a metric between vectors in RD to compare the descriptors, but it's more robust to large-scale curvatures. Okay. So let's have a look at what we can do with this kind of very natural descriptors. So first application would be denoising. So let's try to remove noise, which is included in some scan, which is just a measurement error or some other noise which can come from various sources. So the idea is similar to a principle, the principle of non-local means, which is a denoising principle which was introduced in 2005. And the idea is to denoise a point by considering all points of the surface and weighting their contribution by the similarity to P, to the point we're wanting to denoise. So we capture similarity as the distance between the plane plus height patches around each point. And we denoise, so we have a small trick that instead of denoising the positions, we denoise a vector field which is above a smooth space. We basically decompose the surface into smooth space plus vector field. Smooth space means by definition denoised, and we only denoised the residual vector. And we denoise with this non-local principle. So without going into the details, this would give you this kind of results. So here is an initial point set. Here is a reconstruction, denoising by point set surface method. So this is a 2007 method. So I'm just comparing to basically what was the state of the art when we did this work, which is why you don't see anything more recent. And then you have a bilateral filter, which is still widely used, and you see that this kind of the angles are not as well preserved as what we have for our similarity denoising. So the real strength of this method is to be able to denoise, to remove the noise while preserving small details. For example, here is more striking. You have a noisy scan, and you can remove the noise while keeping all the important details from the point. Okay, let's try to do also something else than denoising. Let's do super resolution. What does it mean? It means that you have a scan which is given at some resolution by, I don't know, like something maybe like a Kinect, for example, and you want to improve the resolution because you're not happy with what came out of your scan. So one way to see that, so the principle we're going to apply here is, you can see it here, is just you have a surface and you have a detail which is only partially acquired on several locations, but it's repeated. And what you're going to do in this self-similarity framework is actually to match the various, the different details to find that they are actually the same one, and aggregate this information together, and then copy paste back the details to the original location. And what is important here is that we're going to use a Quadric+height description, because otherwise it does not provide enough information and you cannot make the super resolution work. So what basically it does, it's matching details, unbending the details and making them talk to each other, and then passing back the enhanced detail back to the original position. So here is the kind of results you get. So you see in particular in this kind of areas here that you have improved a lot the small details, repeated details, and you really have enhanced what was obtained from the scan. So here is another example where you have which is done only as an example of what you can do. You take a high resolution scan, you degrade it, so you smooth it, you downsample it, and you add noise. So you have this kind of degraded shape. Then you compute the quadric super. Okay. Should I go ahead?
Oh, sorry. My internet was not very stable. That's why I probably don't hear
Okay.
you. I just have a small question. So,
Yes, sure.
basically, before when you only have like when you are only looking at the local features,
Yeah.
it's basically just if I understand it correctly, it's basically you would repeat as much as similarity as your neighbors. But in the for the super resolution case, with the improved one, you basically have much more detailed talk communicated across different areas. Is that correct?
Yeah.
Um,
So yeah, actually the for the denoising you would need, it's more or less the same principle. The difference is that so you're going to aggregate details from or areas from different areas in the shape. And for the super resolution, you would add you would need to have to take into account the quadric plus height, because otherwise you don't get enough information from the other areas of the shape. And I trade that answers your question.
yep. It's just a clarification. Thank you.
Yeah, so here you have the initial shape which is degraded, and then you compute the quadric super resolution on the right here, and you see that you get much more details compared to what was previously the case, with other competing methods. So one thing which is important to understand is that it's when you do super resolution, you're not really targeting recovering what was the real signal. What you will really get is what is plausible under your model hypothesis. So my model is self-similarity. So I will produce something under this self-similarity hypothesis. And that's why, I mean, we do compare numerically to the initial shape, but in fact, in a way, it's only partially makes sense. So comparing is just there to give you an idea of how far we can get. Okay, so now we know how to improve a shape, like denoise it or make it better. But there's also a huge problem we can tackle, is the question of how can we encode these shapes? Because having a lot of points is, of course, memory intensive. And since we know that some features are repeated on the shape, maybe we can just encode them once and try to use the self-similarity to have something very small in terms of memory usage. So why would we encode several times the repeated detail instead of just once? So this basically is the idea of this work. And the way we do that is to say that we have this sampling of a shape. We cover the shape with patches, with small, we basically subsample a set of points, and we compare the neighborhoods. We parameterize and compare the neighborhoods. And from this description, the descriptions, we compute that, we decompose them on a small dictionary combined with a sparse set of coefficients. Small dictionary meaning only 16 or 32 atoms. So it's very small compared to maybe 200,000 patches. And the set of coefficients is sparse. So it's actually quite efficient it's actually quite easy to encode them, because sparsity is good for matrices. And the real important thing here is how do we go from patch descriptions to coefficients plus dictionary? And this is a problem which has actually been studied a lot in machine learning and in computer vision. And the goal is to find a dictionary composed of a certain number of atoms, over which a descriptor would be represented as a sparse, so a lot of zeros, linear combination of the dictionary atoms. And in an optimization, if you write that as an optimization, it's just right as finding a dictionary and a sparse set of coefficients subject to having not so many non-zero coefficients. And this is a very hard problem, which is which cannot solve, it cannot really solve it, but we have some greedy heuristics to approximate a solution. And in particular, we have the KSVD algorithm, which can which alternates between sparse coding and dictionary update, and manage to find an approximation for this minimization. So combining that with further compression, seeds position compression, parameterization compression, coefficients, efficient coefficient representation, we can just encode we can just really make it use it for compression. For example, here you have a scan of 10 million points, and you compress it to 2.5% of its initial size. And the error you do is actually less than 0.01 millimeter for an object which is around 30 centimeter wide. So it's the error we're committing is actually quite small. And furthermore, what you can see that what is actually being removed from the data is noise. It's kind of scan superposition noise, which is completely removed from this from the decompression. So left is the original data set, original data, and left is the compressed plus decompressed. And you see that what you recover the shape very well, and what you remove is only the set of the kind of small noise which was in the initial data. And that's a way to look for self-similarity, which is actually implicit, meaning that you're not actually going to say this patch is similar to this patch, but you're going to say both patches can have can decompose, can merge into a dictionary, in which they will enhance the similarity. Similarity will be enhanced, and that is due to this sparse assumption, small dictionary plus sparse assumption, which makes the similarity tend to collaborate in an implicit way, compared to the two other methods I showed, where self-similarity was more explicitly looked for. So if you compare to standard point set compression techniques, you'll see that you get much better results for a number of bits per point, which is much lower in our method. Okay, so all of that works quite well, but there's a catch, of course, which is that if you have a point set which has open boundaries or small features, then everything will break. So on the top, you see on the bottom, you see the original point set, and on the top, you'll see compressed plus decompressed. And you see that we have completely lost the small features here and more in the lines. Why is that? It's because you make the assumption, you assume that everything can be parameterized. So basically, your surface can be parameterized locally on a disk. This is one of our working assumptions. And of course, when you have linear data, like you have wires in the street or things like that, it will break because it does not satisfy this condition. So sometimes assuming that you have always a surface is not the right way to go, and you would need something a little more, a little better. And that's what I call mixed dimension shapes. And the best way to look at that is to look at this boat. This boat is more or less, it's a shape, it's a surface, it's a set of surfaces. If you would have an infinite precision laser scanner, you would see that the riggings are actually surfaces. But at the scale at which we're applying it, it's much more interesting to look at them as lines. So you have a set of surfaces here, And here on the rigging, you have a set of lines. And so the dimension of your data is varying. So we need to find, for these cases, a descriptor which is able to handle them, to handle both of this kind of data. And the way we addressed it was to move from smooth surface plus height description to vector field description. The idea is that you would have, similarly to before, an idea of a small disk which are spread on the surface, but instead of having a height field on this disk, you would have a vector field, meaning that it can actually degenerate. And this kind of this here, although as you see here, you have a line. Well, it's just a picture, it's just to give you an idea. But here you have a line, and you see that all the vectors tend to converge to the line, so that the vector field degenerates. So in a way, it's a kind of a generalization of the Plane+height vector description. So instead of encoding the shape, we encode a set of deformation fields. So this is not really what's important here to understand is that the only thing you'll need is something which will attach a point to a point on the surface. So an operator which will say on which for a point in the ambient space, so the R3 space, so space, on which point to which point on the shape it would be closer. And what we used is basically a nearest point projection. And now you have a different descriptors. You can still use the same ideas, meaning that you can still try to highlight shape similarities by using a joint analysis of the local, what we call this local probing fields, so these local vector fields. And to do that, we will use something similar as for the compression work. We look for a small dictionary of atoms, a sparse set of coefficients. And what is original here, what is more new, what is challenging, is that we will also try to make the positions and the orientation of these vector fields better to enforce a consistent representation. So mathematically, it yields for an optimization problem with a decomposed. So here is what we want to do, the vector fields. Here is the dictionary and the coefficients. So you try to minimize the representation error. So how far is your dictionary decomposition with compared to your vector? And here to your to initial vector. And here you have a something which enforces sparsity. And this is kind of the original standard optimization work, optimization problem. What is new here is that we also try to improve the representation themselves. And for that, this builds a non-trivial representation optimization problem. So it can still be solved in an iterative fashion, alternating between dictionary learning, post-optimization, and update of the representation. Both first steps make the optimization decrease, so the energy decrease, so that's fair. The third one can make the position can make the energy increase a little, but still overall it will, in practice, it decreases still. So you have a nice energy minimization in general. So let me show you a small example. Wait, I need to do that. Show you just a small. Are you seeing the? Oh.
Yep, and I see the video.
Sorry.
Not now.
This is not working. Yep, it's working. Sorry, here. So let me go back to the beginning. So here you have a set initially of vector fields of which are aligned completely randomly on the surface. And then you let them evolve according to this optimization. And what happens is that the vector fields, the parameterizations tend to align so that similar things get represented similarly. And of course, it stops. Yep. So in the end, whoa, sorry. Well, you get the idea. Let me just share again that you will see. So here in the end, you'll see that all the representations tend to align correctly. And so that similar things get represented basically similarly. And this is the atom, the main atom that comes out of the dictionary, in which you can see that it's more or less a part of the sinusoid. So it's completely a toy example, but it shows you how optimizing the position of these vector fields, of these small deformation fields, can help you find similar things. Okay, so that's good for analysis too. If you take this hollow cube with a curve crossing it, and you look at what comes out of the decomposition, you'll have, well, basically atoms that represent the edges, and atoms that represent the curve. And we can apply that to resampling. So you can resample point sets while keeping boundaries and trying to preserve small details. So now you don't have any boundary destruction. And you can also resample this boat example. And you see that here you can you respect the initial distribution. You do not overblur it as would you do not overblur it as would any the competing methods. You can also apply it to denoising, so I'll be quite quick about that, by combining it with a data attachment term and the fact that you should denoise your representation. And here is the kind of results we get. So here is a standard, well, it's actually a surface, so it works okay. Doesn't work much better than competing methods, of course, but it's not what it's made for. What it's made for is this case, it's kind of cases here where you have both surfaces and lines. And if you add noise to this kind of data, then basically this is the only method that is able to recover both the net and the surface. Okay, so maybe I have 5 minutes more to do this.
Yeah, and however you want. I think we can go a bit longer as well.
Okay, so I just try to be quick about the rest of the my presentation.
Actually, I have one small question.
Okay, yeah, please.
That's okay. So I think for the previous section, it kind of mentioned like this multidimensional thing. Would it be because so far the example you showed only I think in grayscale. Is it possible to have more information when you have more color and dimension?
Actually, there's no, well, with this kind of presentation, you could go to higher dimensions. But it's really, the way it's designed, it's still to encode some geometric data. So you could encode a manifold in higher dimensions. If you have a texture on your surface, I'm not sure it will really help. Well, you could. It would require some other tool to include that in the similarity search, because here it's really based on how you deform a field toward your shape, and if your shape has colors or any other information, then I think you would need to incorporate it in another way. So it would require some different extension, I think. And here the color I show is just a normal it's just basically the normal to the surface. It's just a way to, we call it a normal map. Basically, it's just a way to just a way to make it better looking, basically.
Yep, makes sense. I was just wondering because sometimes maybe the color would provide some more information or something, but yeah.
Yeah, actually, I think it would make more sense for the part where you have a when you want to aim to compress, or you want to do self-similarity, to do super resolution, because there it could really help to maybe disambiguate between things that are really similar and things that are only partially similar. So yeah, it could really be helpful. So my focus here is more or less on geometric data, but it really could be extended to data with color or yeah, any other information you can think of.
Thank you.
So here I'll just talk briefly about some other work we'll be doing more recently. So let's forget about self-similarity and try to be back to what is a surface. And a surface is basically, well, mathematically it's defined as locally you can parameterize it by a 2D, well, a surface of dimension 2 in 3D. Locally you can parameterize it over a small with respect to a small subset of R2, and so it's basically a plane+height vision of the surface, where the height is encoded as z equal f of x and y. And the work we did was to try to find a shape, a basis, a function basis, which would be helpful to analyze these kinds of the kind of functions we get when we look at them, when we look at the surface. And the idea we have is to decompose a surface into basically standard shapes like a paraboloid, a monkey saddle, a horse saddle, and basically that is an anti-symmetry. So the idea is to just decompose a shape to find a relevant function basis. And the way what we wanted to do is to try to enhance how frequential information, like the way that the surface evolved in an angular fashion around each point, and how the surface would evolve away from the point. So it's both, so radial, basically radial plus radial decomposition, and this can be just we can prove that the surface can be written as is. So it's just some kind of Fourier decomposition with respect to the angle, and a polynomial decomposition with respect to the radius. So the basis has this nice property that it separates between a radial evolution and an angular frequency component. And if we look at what the function look like, we have a plane. So 0 oscillation and 0 evolution on the radius gives you a plane. You have a paraboloid, horse saddle, and anti-symmetry, and you have a monkey saddle as well. And these are shapes which are very famous for geometers, and that's something we like because we can relate them to something to important geometrical features. So, for example, here you have this the point here on this shape, and you can decompose it as this kind of shape of basis shapes, and of course they have some weights which is weighting the different contribution. So it's more theoretical work, but we can show a lot of nice properties. For example, if you made a mistake when you found the normal, then you can just correct it very easily. You can assess which angle, what was the mistake you did, and you can correct all the coefficients to get the corrected coefficient. So it's actually quite interesting numerically. And you can relate it to various surface values, such as Gaussian curvatures, mean curvatures, and so on. So it's something we like for shape analysis. And the way we finally, so that's for the theory, practically the way we do that is just by trying to fit. So it's just basically a fitting process where you try to fit the function basis, truncated function basis, to a set of neighbors of a point P. And you can actually solve it using a QR decomposition. It's just a minimization algorithm, a minimization problem which can solve using a QR decomposition. And the application we did was for detail enhancements. So what we will try to do is to increase how much the point deviates from the tangent plane, or how much the normal deviates from one point to its neighbor, so to increase the contrast of the shape. And for example, here is a shape for which we will try to increase using our basis. We should try to increase to increase the contrast by moving the points, and just by modifying, looking at the basis, we can get this kind of result here, which, well, you see the braid is much more sharp, the hairs as well, and you can do the same for the normals. So here it's a little trickier to just modify one of the coefficients of the decomposition. And what's important here is that actually the points don't move. It looks more sharp, it looks sharper only because the surface normals changed. And it's in a way it corroborates what we already know, that we as humans are more sensitive to normals than we are to actual positions. And for rendering, it's something which is well known, but I just wanted to remind it here. And yeah, so you can enhance the normals. And you can actually do something interesting, which is comparing both normal-based and detail enhancement and position-based detail enhancements. And you see that actually normals work quite well. The only thing is on the silhouette, on the outline of the shape, since points actually don't move, there's nothing will happen here. The points will keep their positions. And if you look at what happens with positions, position-based detail enhancements, you will see that there is much more enhancement, but something happens on the outline because points are actually moving. Okay, but with normals, you can do something much more funny. You can try to skew the normal orientation, meaning that you can try to rotate to give the illusion that the shape has rotated. So here is just a shape enhancement, and then I will use a complex gain to make them to change the normals. And here, once again, nothing, the points didn't move, only the normals. Here you see that, well, it changed completely the way we perceive the shape, right? Now, you can also try to invert details. So here you have enhanced the details, you have them moved, make them more sharp, make them sharper. And if you inverse the details, then you get like as if the details were going inside the shape instead of outside. And well, yeah, that's basically what we can do with this basis for detail enhancement. Let me just give you a small idea of what we can do if we go into higher orders, that's more recent work. And usually we stop at order 2 for our shape analysis. We stop at curvatures, basically. But higher orders can actually contain valuable informations. And the way we know that is that there was a whole thread of work, which was done in the early 2000s, which was detecting ridge and valley lines. And if we want to look at, if we want to define tensor of a differential tensor on the surface, so we can see that actually it can work quite well given our with this basis. So once you have the coefficients, you can compute any tensor, differential tensor on the surface. And it means that you're going to be able to analyze better the shape, like extract curved lines, ridge lines, valley lines, just by looking for certain directions which satisfy some properties. And we can also generalize principal curvature directions. For example, this gives you this kind of result. So curvature directions basically give you the way, the directions in which surface bends most and the surface bends least, and both are orthogonal. And here, so I just represented the maximum one. And if you go higher into order, you've brought the principal directions of dimension 3. So using the differential tensor on the order 3, you will get the corners. You can get characterization of corners in the shape. And this will help you, this can help you build better meshes or just simply do the analysis. Okay, so you can do that on much more complicated shapes. And so it's really more of a theoretical work, but I think there are still some applications to be found. So let me just conclude briefly. There are many facets to shape analysis. I presented some of them, but it's just a small subset of what we can do with shapes. It's in a way, it's data-driven. The first part with self-similarity was data-driven, even if it's restricted to a single shape. And we can extend it to data sets to be in the new machine, well, not so new, but in the famous machine learning, deep learning trend. And there are many more topics to tackle in the coming years. And I think it's a very exciting field. And yeah, it's a good idea to keep an eye on it anyway. So thank you. And I hope I didn't go too much over time. Yeah, quite a lot. Thank you. And I'd be happy to answer any question you might have.
Very nice talk. Does any of you have any questions? I will first stop the recording and then you can basically ask any questions you're interested in.